Good morning, good afternoon, good evening, ladies and gents. This is Sarah van Grinnen, aka Mr. VG, and I am excited to be here with you. You will realize that I love to say that because maths makes me excited. Maths makes me come alive in the day. I know that some of you are a bit envious or thinking, yo, this guy's a bit weird, but this is me. I love this. So what I'm going to share with you today is a video on Theorem 2 of grade 12 geometry. Now this specific example is a numerical example, and I know some of you guys are craving a video about riders, and so how do I approach riders? But I promise you, when we do our live session, I will do a few examples of Euclidean geometry riders, where we have no values, just show that this is x, or show this side equal to that side, or this side over that side, something like that. I promise I'll do it in the live session. So when we have a look at this specific question comes out of a grade 12 IEB paper. I chose this question, although it is a numerical question, I chose it because it is a lovely example of how we can mix up different parts of our curriculum. We are going to use grade 11 geometry, we are going to use grade 12 geometry, and we are actually going to use some trigonometry in here as well. So before I get too excited, buckle up. Let's dive into the specific sum. Let's go through this scenario. You will see that I approach it in a specific way. And if you haven't watched the Euclidean Geometry video of mine yet, I encourage you, go and watch those videos. Go and check those videos out, because those videos will share with you exactly how I approach geometry a bit differently maybe than what you are used to. I am going to approach it by first of all working through all the theory before I even look at what the question asks me. Because I can practically guarantee you, if you can do that and you can write it down proper, you're going to score 70 to 80% of the marks already and answer 80% of the questions. So let's dive into this question and go through the information. In the diagram below, N is the center of the largest circle. So in other words, if I look at the sum, Cn is equal to ND, which means I've got an isosceles triangle, which gives me that angle C, and angle CDN is equal. Also, that little angle at the center, angle N, is twice angle E. That is Theorem 2. I'm not going to look at Theorem 1 because if I look at Cn, that line there, I don't know anything really about that line. I don't know that the radius ND is perpendicular to it or it bisects CE. I don't know, so I'm not going to use that. I don't have a diameter, so I'm not going to use Theorem 3. Let's carry on to the next bit of information. And M is the center of the smaller circle. Same procedure. M is equal to MB. And also, I have an isosceles triangle. So that little angle A and that little angle B will be the same. I don't have any more info about that, so let's read the rest. C, D, E, and M are points on the larger circle. Sometimes I would look at that if I had a cyclic quad, but I don't, so I'm going to carry on. AB is a chord of the smaller circle. I don't have anything about chords more than what I've got already. Next up, they tell me angle AMB is 136, and therefore that little angle A is 22. Now you might just ask me, but so where do you get that? Remember that angle AMB, that little a and that little b that's blue, together has to be 180. So angle A and angle B must be 44, divided by 2, both of them must be 22. Now, I'm not worrying about reasons at the moment, but I must just keep that in the back of my mind if I need it. I'm going to come back to the angle DEC being 22 degrees because I want to just work in that small circle for a moment. So angle, or they say AN and NB are tangents to the circle. So first of all, a radius perpendicular to a tangent. So in other words, angle A, that whole angle A and the whole angle B must be 90 degrees, and therefore angle BAN is 68 degrees. Fantastic, I'm getting closer and closer to this. Theorem 6, or Theorem 7 I've done now. Theorem 8 says if I've got two tangents from the same point, they are equal in length. Let me just put an extra little line there, just so that you don't get confused that I'm using double lines more than once. But that also means now that angle ABN is also 68 degrees because there's another isosceles triangle. Now, for those of you quick thinkers, you can actually see that NAMB, yes, is a kite. I'm not really going to use that, but it's something just cool to look out for. Now, lastly, to finish off this part in the red here on the left by the small circle, I can get the size of angle ANB, which is 44 degrees by looking at interior angles of a triangle. Now, to go back to the green part, so the bigger circle, I'm now going to look at angle DEC. Now, angle DEC is 22 degrees. This means that angle CND, is 44 degrees. I'm going to repeat the exact same process as I did in the small triangle, and I can find that angle CDN is 68, as well as angle NCD 68 degrees because of interior angles of a triangle. I have now exhausted the most of the information. You will see that I'm not touching CE is 9 units and DE is 6.2 units at the moment because I looked kind of ahead, and that's more going to come into the second part of this question. So what is the actual question now asking me, now that I've got all my information? It says prove that triangle ANB, so in other words, this triangle there, is similar to that triangle there. In other words, I need to prove that angle A is equal to angle C in that triangle. They're both 68 degrees. I've got to prove the two ends equal, and they're both 44 degrees. Amazing. And lastly, I need to prove angle B is equal to angle D in those triangles, and they're both 68 degrees. So the triangles are actually similar. I've actually done it without knowing that I do it. But now I need to actually write it down. So what I'm going to do now, guys, is I'm going to step by step write down. I'm going to start somewhere. I'm going to start by saying that AM is equal to MB. Guys, I'm now going to just, whatever I did earlier, I'm just going to write it down. Therefore, angle MAB is 22 degrees because it's interior angles of an isosceles triangle. This means that in triangle ABN, that angle A is 68 degrees because of tangent perpendicular to the radius. Now you will see that I can use angle A just as that because I did specify to the examiner that I'm working in triangle ABN. be careful. You cannot just say angle A is 68 degrees without specifying triangle ABN. Because otherwise it means it's the whole 22 degrees and 68. So please remember that. What else do I know in triangle ABN? I know that AN is BN because it's tangents from the same point. As well, I know that angle B is 68 degrees because of angles opposite equal sides. And therefore, angle N was 44 degrees because of interior angles of a triangle. Now I need to move over to the second triangle and see how do I work in CND. Well, first of all, I know that 2 times angle E is equal to angle DNC. So it's 44 degrees because of angle at center equal 2 times angle at circumference. Next up, I know that CN is equal to DN because of radii. And therefore, angle C is equal to angle CDN, 68 degrees, interior angles of an isosceles triangle. Just have a quick look. I didn't say just angle D, I said CDN. Because I didn't specify that I'm working in a triangle CDN. Be careful of your way of writing. Let's now go and see. Okay, I want to finish off this sum. So I'm going to look at the similarity. So in triangle ANB and triangle CND, firstly I have angle NAB is equal to angle C, 68 degrees. Secondly, I have angle ANB equal to angle CNB, 44 degrees. But I mustn't forget to write that this has been proven. Lastly, angle NBA is equal to angle NDC, 68 degrees, also proven. This will finish off my sum, and therefore triangle ANB is similar to triangle CND because of angle, angle, angle. Remember that this third little point, I could have also used interior angles of a triangle for the third set of angles in similarity. You don't have to have another reason except interior angles of a triangle. So what we are going to do now is we are going to look at the second part of this question. The second part of this question, I now mustn't forget what I have proven already. So when we have a look now at the second question in this specific one, the B part, it asks me to calculate the length of AB. So there is kind of where I need to go. So if dn over an is equal to 27 over 25, calculate the length of AB. So let's quickly just go back to the information that was given to us right at the top. So those three little bits of information which was not given to us, or we haven't used it already. So let's first of all look at this first bit. They tell me that CE is 9 and DE is 6,2, as well as that little angle in there being 22 degrees. Okay, that's going to be very, very handy in the next coming lesson. So when we have a look at this specific question, let's start at where we are actually at the moment. So we have proven so far that triangle ANB is similar to triangle CND. That was proven in the A part. Very important lesson for us today. We do not want to forget what we have proven already. Because we've proven this, it means that actually I can deduce the ratios that AN over CN is NB over ND, and this is equal to AB over CD because of the positioning. That one that I circled there, AB, is the one that we want to get to. So I know that that is the one ratio I do need to use. So when I look at this, ladies and gentlemen, I'm going to use AN over CN equal to AB over CD. I am not going to use NB over ND because I know nothing about those specific sets of lines. Next up, I'm going to look actually at what was given to us. What was given to us is that DN over AN is 27 over 25, which means I'm going to flip it, I'm going to reciprocate it, to actually get to something similar to that AN over CN that we were looking at. Because AN over DN is very, very similar to AN over CN. So, what do we know about DN and CN? Well, they are equal because they're radii. They're radii, and therefore I can say that AN over CN is 25 over 27, which is fantastic because that is what I have there at the top. So now I'm going to introduce that AB over CD for me to actually get to the line length of AB, because remember, that is our end goal. At this moment of time, we just have to hit the pause button. Now, it's not your pause button on the video, but my pause button. Before I go further, I've got to now just look where I am. I want AB, and I've got it to AB over CD to be 25 over 27. So, in other words, if I can get the length of CD, then I can get the length of AB. But how on earth am I going to get the length of CD? Well, the cosine rule. Look at that triangle, the purple one there. That purple triangle there. I can use the cosine rule. Oh my goodness, I didn't know that I can bring in cosine rule in Euclidean. Well, nothing is stopping you. Nothing. You are allowed, and they're allowed to ask you anything from paper 2. Mixed together, jumbled up, thrown together, they can ask you anything. So now, let's look at determining the length of CD by using the cosine rule. Well, CD squared is 9 squared plus 6, 2 squared minus 2 times 9 times 6, 2 times cos of 22 degrees. So therefore, CD 15,96 ... inside the square root. So it's very, very close to 4. Actually, it's 3,999 or 996, I think. In practice, you please mustn't round off. So actually, you should have kept it as 3,99. But today, it's okay. So let's just multiply by 4 on both sides, because if you just wonder where I got that from, remember, I'm bringing this all the way down from there to there, and I've substituted CD with 4. I'm multiplying both sides by 4, and therefore AB is 3,70. I would have loved for you to rather use the 3,99 ... and your answer would be very, very, very similar to what I got. Ladies and gents, please do not forget that they can ask you anything mixed up. They can ask you sine, area, and cosine rule to calculate the length of a side. Now, I promise you, in the live stream that I'm going to do, this specific video will open up some things for you to see that I can mix everything up. Grade 11, grade 12. But in the live videos, I am specifically going to do geometrical riders. So I'm not going to look at sums like this, where I bring in values and magnitudes of angles. I'm just going to look at those ones where they tell you, prove that this is equal to X, or prove that side equal to this side, or prove a cyclic quad. So ladies and gents, my encouragement to you is to not give up, to not throw in the towel when you see that I'm mixing all of these things together. Yes, this was a really, really tough question. Yes, it was left field because they brought in analytic, or they brought in sine area and cosine rule with Euclidean. They will do that. They love to do that. But don't give up. Remember to subscribe. Hit that notification button, and you will receive all the newest videos. You will receive notifications of all of the things that we post on the Junior Tukkie YouTube channel. So go and have a wonderful rest of your day, ladies and gents. Remember, you are awesome. Keep well. Cheers.